a lot of it is about Chernoff. Okay, so we're going to do a couple of examples of Chernoff, and then we're going to prove Chernoff bound 2. We're not going to prove Chernoff bound 1, just number 2. All right. Lottery payouts. All right, so we have this game where you pick. Okay, so you pick a 4-digit number, something between 0 and 10,000. And if the lottery picks your number, you win $5,000. Okay, so your chances of winning are 1 in 10,000. So your expected return on your $1 is 50 cents. Okay, so the lottery expects to earn money on this, but there is a disaster case, and the disaster case, of course, is that you end up paying out a whole bunch of money that you weren't expecting to. Okay, so for example, if 10 million people play, the number of expected winners is 1,000. But if 2,000 people won, then you would break even. If more than 2,000, then you would end up losing money. Okay, so how extreme an event is this? Okay, so we're going to use the Chernoff bound to figure this out. We could use some other bounds, but Chernoff really shines when the expected values are large. Okay, so this is just the general rule. When the expected value is large, it tends to outscore Chebyshev. When it's small, maybe not so much. Okay, so just to remind you what the Chernoff bound looks like. Okay, so if you can set up the problem to be the sum of n independent t's, where the t's are between 0 and 1, and they're all mutually independent, then you can bound the probability according to a multiple of the mean, and it grows sort of exponentially as a multiple of that mean, where there's this beta factor here that scales according to c. Not quite c, but c. Okay, so I'm just going to keep this thing around for the question, and probably the best way to do that is to just fold that over. Okay, so there we go. Okay, so how do we set up the problem? We set it up exactly like this, the sum of all t's. Okay, so solution, we let t be the sum of the results of n tickets. Okay, and we can just make this a binomial. That's a pretty classic way of dealing with this. Okay, so the total number of winners in n tickets. And then we want to know what's the probability that it's, there's more than 2,000 winners. And, 2,000 happens to be a multiple of 1,000, right? Okay, so what's the multiple? That's c. C is going to be equal to 2 for this. Okay, so since 2,000 winners would be twice the expected number, we use c is equal to 2. And I calculated this beta of 2, okay, because we need to calculate this thing. Okay, so beta of c in this case is around 0.386. Okay, so the rule here, so we want it to be a multiple of the average. Okay, so the probability that t exceeds 2,000, which is 2 times 1,000 basically. Okay, so this is the probability t is greater than or equal to c. No, I really clean that up. That's sort of our mental picture here, right? This is c, which is 2 expected value of t, which is less than or equal to e to the minus 0.386 times the expected value, okay, which is a very stinking large number. And this is why when your expected values are big for Chernoff, you end up getting very fast convergence, because the exponent here is huge, right? This is e to the minus 386. Okay, so just for context here, like e is like 2.7, you cube e, you get 10. Okay, so you sort of look at the power here and divide by 3. That's the number of zeros you're going to get in a decimal number, right? Well, 0.00000. So it's a very, very, very unlikely event to occur. Like the cosmos will probably spontaneously combust. It's probably more likely than this. Okay, so this is a sort of a vanilla example you might use Chernoff for. And we're going to do a more complicated one for one computing application. I was going to do two, as some of you got the notice this morning. A/B testing is very similar to this analysis, this randomized load balancing, and we don't get much. We don't get much for it. I mean, it's interesting and whatever, but the analysis, the convergence is. I mean, it's similar to the voter poll, not the randomized load balancing. But we don't get much out of it that's extra. So we're going to do something else instead. Okay, but this is going to be our other big example for Chernow before we go in. Okay, let's get to it. First, the problem. Okay, so the scenario is a bunch of engineers were sitting around trying to figure out how to deal with a whole bunch of posts. Many posts come in for a social networking site. And if one server takes on too much work, then there's lag, and then people are unhappy. And in some extreme version of this problem, not only is there lag, there are server crashes. Okay, there's just too much stuff, the server crashes. All right. So what do? Well, they sit around and they engineer, right? So they come up with a whole bunch of different ideas, a bunch of different schemes about where to map these various things, and they eventually throw their hands up in the air and say, well, why don't we just assign it to a random server? Okay, so we have M servers around, and we just randomly assign each task to a server. And it turns out that nothing breaks. Okay, so there's a real good question as to why nothing breaks. And we can actually analyze this using Chernow and all the tools that we've got, including one surprise guest that we'll see in a moment. Okay, so anyway, so let's look at the particulars of the problem. And the numbers I've chosen here are nice so that we can conveniently divide integers. We don't need a calculator for this. Okay, they might not be so nice in real life, but let's just deal with it. Okay, so there are 2,400 forum posts in every 10-minute interval. So over a 10-minute interval, a server can handle 600 units of work. Okay, so 600 units of work, okay, so in a 600-second time interval, and it turns out that the average post takes a quarter second to post. Okay, so that's kind of an average. It's no worse than 1 second, and of course it has to be at least 0 seconds to, so somewhere in the interval from 0 to 1, which again is good for Chernow. Okay, so that's another thing that we're going to use for Chernow. Anyway, because it's an average of a quarter second and there are 2,400 forum posts, the average total amount of time in a 10-minute interval is, I guess, 1/4 of this 24,000. So that's 6,000 seconds worth of work in total. Okay, so just back of the envelope calculations here. And 6,000 seconds worth of work, each server can handle 600. Okay, so we need at least 10 servers. Okay, so if everything was perfectly balanced and everything was perfectly distributed, 10 servers would get the job done. Of course, if anything is just a little bit off a hair one way or the other, the server, there's probably going to be a server that's going to crash. So probably we need at least 11 servers, right? Okay, but the question is, how many servers do we put in there where we get confident? Okay, where we get confident that nothing's going to crash. Okay, so everyone understand the problem? Okay, so we need at least 10 servers according to this. And we're going to look at some, quick calculation using Chernow and see what's the likelihood of things crashing with 11 servers and 12 servers, 13. Okay, and we're going to pick a number that we're going to be happy with, and you're going to see that this thing converges really quickly. Okay, so let's go on. Okay, so our job is to figure out how M affects the reliability of this. Okay, so determine M, the number of servers that will make our lives happy. And in our analysis, we're just going to focus on server number 1. We'll get to the other servers in a moment, but we'll just focus on server number 1. All right. So server number 1. From server number 1's point of view, there are a whole number of jobs that are out there. I don't know how many there are. It says, we do know how many there are. 24,000. Okay, so there are 24,000 jobs, and how much work does server 1 do in total? Okay, so we let TI be the number of seconds that server 1 spends on that job. Okay, each of the jobs numbered 1 through 24,000. And if it happens that job is assigned to the server, that's how much it gets. And if not, it spends 0 because some other server is doing it. Okay, so there's probably going to be a lot of zeros in this summation. Anyway, this is the quantity we're going to go after here. Okay, we're going after the total amount of work assigned to server number 1. Okay, a lot of them are going to be zeros if they're not assigned, but there are 24,000 things. And just as before, remember, the more times you sample, the faster the things converge. Okay, so this is going to be, you'll see how fast it converges. All right, our goal, find an upper bound on T is at least 600. Okay, so that would mean the server is at capacity or over capacity. Now, each of the jobs is between 0 and 1 second. All of them are independent, so we're going to use the Chernow bound on T. Okay, so and I'll keep this puppy handy. Okay, so we're going to use the Chernow bound on T. We need the expected value of T. Okay, for this thing to work. All right, so what's the expected value? Well, this is equal to the expected value of the sum from I is equal to 1 to n of T sub I. And we can use linearity on that to just pull out that summation. so the question, what's the expected value of Ti? 1/4? Okay, how'd you get that? It's not quite, yeah. So if you look at the problem, it says each post costs an average of 1/4 second. I agree with that. A quarter is going to be involved here, but that's not the whole story. 1/4m, yeah. Why is there an m in there? Right, so you have to multiply by the probability it actually gets assigned to that server, right? So 1/m of the time it is assigned, and the other m minus 1/m, it gets assigned somewhere else, so the amount you spend is 0. So you have to use sort of this law of total expectation calculation. We're not going to put in the 0 times the other probability because the line will get a little bit too crowded for my taste, but you need to multiply by the probability that it is assigned to the server. Okay, so it's I equals 1 to n of 1/4 times 1/m. It'll be 0 times the other probability in the other case. Anyway, okay, so n is 24,000, so we're multiplying 24,000 by a constant. And that's 6,000 over m. And that sort of makes sense, right? Because you have m servers, you have 6,000 amount of work. You expect each server to have 6,000 divided by m of it, right? I mean, that sort of makes sense. Next. Okay, so we have the essential elements of the turnoff bound. Okay, so we use the turnoff bound. Okay, so the probability that t is greater than or equal to c times the expected value is less than or equal to e to the minus beta c e of t. Okay, so I just copied that off. We don't need to say more. Okay, and the thing that we're after here is greater than or equal to 600. Okay, so that's the thing that we have to make that thing look like. So we have to find c for when c is t is equal to 600. Okay, so since c, expected value of t, is equal to 600, then we can solve for c. Okay, so c, we know what e of t is 6,000 m, sorry, 6,000 by m is 600. Okay, so we can divide both sides by 6,000 over m, and this gets us m by 10. Okay, so we can back substitute in. Okay, so we get the probability that t is greater than or equal to 600 is less than or equal to e to the minus beta of m over 10 multiplied by 6,000 over m. Okay, so this, just pushing pause for a second, this is the probability that server number 1 is overloaded. Okay, so far so good. Okay, so all we're doing is we're finding the multiple of the means here to get us up to 600, and it's going to be a function of m. We're going to try some different values of m in a moment, okay, but we need to do one more thing. Yeah, so this is an upper bound that this is greater than or equal to 600. Yeah, so we don't know that it's exactly that probability, but you're going to see that this value gets really, really small really, really fast, so it's going to get close to 0. Yeah, that's our goal. Okay, good. All right, the missing piece. Okay, any of the m servers could be overloaded. Okay, so that's the probability that we are after. Okay, so it didn't ask us to, what's the probability one server, or server number 1, pardon me, is overloaded. It's any server is overloaded. So written longhand, this is the probability that server number 1 is overloaded. Or server number 2 is overloaded. Or number 3, or number 4, or I can probably squeeze number m in there. Which is not easy to calculate, right? Because it could be that 2 of them are overloaded, 3 of them are overloaded, and so on. And they're not independent events, unfortunately. And that's pretty easy to see. If one is overloaded, then it's less likely that another one is overloaded. And suddenly this becomes very complicated. It doesn't have to be, and we can relieve our complication by using a trick. And I sort of told you about this trick, and we have used this trick once or twice before, but it hasn't come up very much. It comes up a lot in questions like this. Okay, and the trick is to use the union bound. Okay, so the chances that any of these things occur is less than or equal to the chances of one of them occurring plus the chance of the next one occurring, and so on. okay, plus, okay, and this is by the union bound. Now, there's nothing special about server number 1 in this calculation up here. In fact, this analysis works the same for all of them. Okay, so they're all the same chances. So it's going to be the same chance. Okay, it's m times whatever we got up here. Okay, so this is equal to m times the probability server number 1 is overloaded. Okay, so just taking that as an aside, we want the probability that no server is overloaded. Okay, so thus the probability no server is overloaded is 1 minus this. Okay, so we're going to take this, multiply it by m, so this is m, e to the minus beta m by 10 times 6,000 over m. Okay, so that's just a little bit of math, all right? We've derived an expression that is, it's a lower bound on no server being overloaded. And, we did some approximations as we were going in here. I mean, the turnoff bound is certainly not a tight bound, and this union bound is certainly not tight. But, we can try some values of m and see how good things are. Yeah. Okay, so if we have just 11 servers, the probability is greater than about 22%. Okay, so this value here ends up being 78.4% that one server or more is overloaded. Okay, and that's not very good, right? You don't feel so secure about 11 servers. What about 12? The chance of failure is bounded above by about 0.1%. Okay, so you have 99.9% reliability using this sort of coarse approximation. So just 3 nines, all right? So that's pretty good, and you should probably feel pretty secure about just using 12 servers, but if you want more reliability, you want more nines, here's what 13 looks like, 0.000000076. Okay, so you end up with 7 nines of reliability with just 3 more servers than, minimum. Yeah. Cool? Cool. Any questions about this one? Can you just use the complement rule? I mean, if you use the complement rule, you end up with an anding in here instead of, so that's what we do when we have independent events. So you have the complement of, server 1 is not overloaded, server 2 is not overloaded. And then I don't know what to do from there because these events are not independent, right? What's that? You can't multiply them because they're not independent. Yeah. So you can do, I don't know what you would do from there. It's a nice idea though. Like anytime you have independent events, you should definitely do that. It's more exact than using the union method. Thanks for that one. Other questions? Okay, let's take a bit of a breather. Okay, so the last couple things that we introduced were pairwise independent sampling, the weak log large numbers. Somebody asked a question about convergence to the, regression to the mean is similar to this convergence. It's not a term I was familiar with, but I did some looking into this, and yeah, it does have a similar feel to the thing, right? So if you have something that is, you do a bunch of samples and you end up sampling something that's fairly extreme, like you do, 10,000 coin tosses and you're ahead in heads by 100 or something like that, that would be a pretty extreme event. You would tend to say that the next 10,000 will probably be somewhere closer to the mean. That's sort of what it's trying to say. Anyway, convergence ends up, you end up getting this convergence. You can use turnoff bound and you end up getting something else, in those cases where that works as well. There's the conditions here are a little less stringent than turnoff though. Okay, Chebyshev though definitely has the square in the denominator, so that's kind of cool. The 2 turnoff bounds. Somebody asked a question in the online forum. I know you'll read it in time if you haven't read it already. Should we use turnoff bound 1 or turnoff bound 2? Turnoff bound 1 is a special case, and you should use it whenever possible because if you use this case, it ends up giving you a better convergence than if you use bound 2. Okay, so that's up to you to decide if you're allowed to. You can apply bound 1, but bound 2, you can. It's more generic. Okay, so if you have a binomial that's just a bunch of coin flips, you should do this here. Yeah. No, there are a whole bunch of different turnoff bounds. I'm only showing you these 2. There's another, you see, this one here goes to the tail on the left side. This one only goes on the right side. There's one for the left side as well. I'm not showing you that one. There are other ones. that you can, yeah. So, but just these two, yeah. So this is not a special case. In fact, if you went to go prove this in the way that I'm about to prove this, you would, the steps would be sort of similar, but you would get stuck. Yeah, the technique to get this bound is a little different. Okay, skipping ahead just to the next set of summary slides, which one should you use? Okay, generally speaking, Markov gives the worst, worst approximations, the worst bounds. It only grows as 1 over c, so that's maybe why. But it doesn't require anything. Okay, so it does not require, that you even know the variance. It doesn't require anything to be independent. It doesn't require. Okay, Chebyshev, if you have something set up like these, the sum of all these t's, they only need to be pairwise independent for the variances to scale by their sum. Okay, so that's an extra condition to get these general things to work. So if you want to scale by the differences around this far away from the mean, this multiples of the mean, it will scale thusly. Okay, so if you know the variance, you can do it. And Chernoff requires even more. Okay, mutually independence. The TIs have to be bound between 0 and 1, and you get an even stronger bound. Here it goes down by a quadratic. Here it goes down by an exponential. Generally, the one that you should use is the strongest one that you can get. Okay, so if you can transform the problem into something that works for either one of these, you should. Okay, oftentimes it's a bit of a horse race between Chebyshev and Chernoff, and you'll see this on your assignment when you start bounding things. You'll be like, why does Chebyshev give a better bound than Chernoff? Well, sometimes it's like that, right? Especially if the expected value is small, then that's part of the exponent. Okay, if the expected value is large, that's part of the exponent. So large negative exponents tend to converge a lot faster, right, than if you have small expected values there. Okay, so just keep that as a warning in your hand. But you can try either bound, whichever one that you get is better. You should use it. Okay, but just be warned that you're not going to see Chernoff is not always going to win. Okay, the conclusion of today, I'm going to write out the proof for the Chernoff bound. Any questions about anything before I dig into that and sort of get lost in some algebra? Yeah. No. So the question is, did Chebyshev always look like this? No. This is sort of trying to make it look like what you would see in a Chernoff. Okay, so you're trying to map it onto multiples of distance from the mean. This is the sort of thing you would get because it's like t from the mean is going to be greater than or equal to some multiples of stuff from the mean. So there's already one of those means baked in there, so you end up with a denominator that's it used to be x squared down there, but now it's it's like x minus 1 all squared. But yeah, so this is just trying to make these things look the same-ish. Yeah. So if you had to use Chebyshev on a test, would I accept this as formula? Yeah, sure. Any form is fine. Anything that I've shown you in the slides is fair game. You don't have to really, you don't have to go and prove it and then use it. Yeah, you can just use it. Just tell me where it came from. But, I don't have the slides all that handy, but so if you look at the form, I guess this is good enough. Yeah. So if you look at this is the original form. Okay, so this is less than or equal to variance by x squared. So it's this difference is greater than or equal to x. So if this difference is in multiples of expectation, right, and you slide this expected thing over here, it will give you c times e of t. Okay, so that's the bit that goes into the denominator for x squared. Is that good? All right. This is an interesting proof in that, and I always find some proofs to be more interesting than others. And the way that proofs are presented is sort of what I mean. So a lot of proofs, when they give it to you, they sort of say lemma 1 and then lemma 2, and then they sort of put everything together and say, see, this is really well organized, and I did it, I proved it. And you're kind of left to wonder why they did it this way, or where the lemmas, or why the lemmas came from, what was the impetus to do that. So this proof is interesting in that, I really like it, in that the proof is inside out, or backwards. In other words, we're going to just prove this, and when we get to a step that we can't do, I'm going to put in brackets, this is because of lemma 1. And then we're going to go and prove lemma 1, and do it that way, okay? So that we're actually motivated by the step that we need, and then we go and prove the step that we need later. Chernoff has a couple of conditions also. One of them is mutually independent. That's kind of different than the other things that we've seen, and bound between 0 and 1. Each of those is going to come into its own in a step. Mutual independence is required by lemma 1, and the fact that t is bound between 0 and 1 is required by lemma 2. Okay, so what do we do? Well, you'll notice that exponentials are a big part of this whole thing. And the key step in doing this, okay, so And this is sort of like what we did for Chebyshev. In Chebyshev, we sort of took the left-hand side and then squared it, and and then did something with the square. And notice that the one inequality implied the other inequality, so that's fair, right? The probability doesn't change. The key thing that is done here is instead of taking squares or doing something like that, you exponentiate both sides. Okay, so that's the only really key step of note. And that works, right? You can take an inequality and exponentiate both sides of it. You can also take the natural log of it, because both of those functions are monotonic. Okay, so they obey when you take their when you apply the function operator to both sides. Okay, so exponentials are monotonic. Okay, when I mean monotonic, I mean like a is less than b implies that f at a is less than f at b. That's what monotonic means. Okay, the rest is the same as what we did for Chebyshev, and that's we apply Markov's inequality. Okay, so let's do it. Okay, so the probability that t is greater than or equal to c times e of t is the same probability as if we exponentiate both sides to the c. So c to the t is greater than or equal to c to the c to the e of t, which is a great power of exponentials. And then we apply Markov. Okay, so this is less than or equal to the expectation of c of t divided by this thing in the denominator. Sorry, that's not number one, that's Markov. Yep. Oh, sorry. I got a little enthusiastic, that's why. Okay, sorry about that. Pardon me. You're right. I was going to trip over myself 2 steps later, so I'm glad you caught that. Thank you. Okay, so we'll deal with the denominator in a moment. In order for us to get this beta out correctly, the way the math has got to work out is that the numerator here, e, the expected value of c to the t, is less than or equal to e to the c minus 1 of the expected value of t. Okay, so this bit, less than or equal to this bit, is lemma 1. Now, why do I say that? Well, you can see the c minus 1 of e of t in here. Okay, so that's that bit there. This c to the c times e of t, we should make that in terms of e to the something. And the way that we do that is by taking e to the natural log of that same thing and bring down the exponent. And when we do that, that will give us e to the c times natural log of c times et. Okay, and these are all in powers of e, so we can subtract the exponents here, and we end up with e to the minus c, natural log c, minus c plus 1. And that's beta of c. Okay, so the only thing that really needs to be done here is to prove lemma 1. Okay, so lemma 1 is on the next page. Okay, so it is expected value of c to the t is less than or equal to e to the c minus 1 times e of t. Okay, and I said mutual independence will be used here. Okay, so proof. Okay, we'll use independence at a key step. Okay, so what's the steps? Expected value of c to the t. T is just the sum of all the little t's, so t1 plus t2 plus tn. And by the exponent rules, we can write this as expectation of c to the t1 times c to the t2 times c to the tn. Okay, so there are some rules that you're used to, right? You're used to the fact that if T1 and T2 are independent, then their product, the expectation of T1 and T2 will be the product of their two different things. Okay. You can also prove that it works for any function of those as well. These things are going to run independently of each other. And I don't want to go through a long proof that works for all functions, but it works for this one. Okay. So the products of each of these things will scale by multiplying their individual expectations. And you'll see that, T1, all the T's are bound between 0 and 1. Now, if they're bound between 0 and 1, then they are, or the expectation of that is bounded above by e to the c minus 1 times expected value of T1. Okay, and all of those are there. Now, why can I claim that? Well, that's limit 2. Okay, so that step needs to be worked out by some other math, but this is less than or equal to that. That's the step, and all of them are less, this one's less than or equal to that, all of them. Okay, and if we have that, then the rest of the math is going to work out. It's going to give us e to the c minus 1, because we can multiply all those together, and we'll add up all the exponents. When we add up all the exponents, we can take a common factor of c minus 1, and then combine these things back together to get us e of t. Okay, so that's by linearity. Okay, so everything is just regular straight algebra. So again, this is sort of the nice thing about doing a proof inside out or backwards, is that this will all work out in the end as long as we had this inequality. Okay, so then we just write it out and we try to prove it somewhere else. Okay, so this is hopefully a little bit more motivating than doing it the other way, which would be here's lemma 2 and then here's lemma 1, and no, now we're done. Maybe, I don't know, maybe it's about the same. All right, any questions so far? Yeah, is it okay? Let's do lemma 2. Okay, so the last one here is expected value of c to the ti is less than or equal to e to the c minus 1 e of ti. Okay, and we're going to use the fact ti is in the range 0, 1. Is in the range 0, 1. Okay. All right. Expected value of c ti. Okay, so we're going to expand this thing out to be the sum over all the stuff that's in the range of ti. This is just the definition of expected value. C to the x, that's the value itself, times the probability that ti is equal to x. Okay. Next step is to approximate c to the x. And if you look at the graph of c to the x, I've drawn out 5 to the x down here. Okay. So if you look at the graph of c to the x between 0 and 1, it looks like this. Okay. So 5 to the 0 is 1. 5 to the 1 is 5. Okay. And c to the x would similarly be c. It's bounded above by the straight line. Okay. 1 plus 4x. And in general, if you had c to the x and you did something similar, c to the x is less than or equal to 1 plus c minus 1 times x. Okay. And this is just a linear interpolation formula for this between 0 and 1. Okay, so we sub that in, right? So this is less than or equal to the sum over all x of 1 plus c minus 1x, probability ti equals x. Okay, so this bit here, okay, so c inset. Okay, next step is to break this sum up. Okay, so we'll take this 1, okay, so 1 times the probability of ti equals x. And this bit here will be c minus 1x, probability ti equals x. Okay, so I've sort of run out of time.